Build a hydrogen-like family of orbitals using A.t.o.m primitives. A central pushback sphere producing a strong pulsating pressure, plus torsional filament coil structure that modifies angular behavior. I'll keep the math recognizably quantum mechanical so you can compare to hydrogen, but every key term has an A.t.o.m interpretation. Overview and physical picture. Short, coordinates. Use spherical coordinates r, theta, phi. The eternal field produces a time-periodic central pressure, Pt, that acts like a radially concentrated potential centered on the pushback sphere. Physically, this replaces the Coulomb minus dfrac e4 pi var epsilon 0r attraction with a pulsating confinement repulsion term. Torsion filaments produce an angularly anisotropic coupling, call it a torsion potential, Vtr theta phi, which modifies angular momentum and can split degeneracies, analogous to crystal field spin-orbit effects, but rooted in torsion geometry. We write a single particle wave function, psi r theta phi t. The governing equation is a time-dependent Schrödinger-like PDE with extra non-standard potentials and possibly weak nonlinearity to model couplings between field and torsion. 2. Governing equation, A.t.o.m hydrogen analog, IH bar, frac, psi, partial t equals hat ht with Hamiltonian, hat ht equals frac bar 2 mem, nablet square plus v pushed rt, v-arm torsion, r phi plus v-arm l psi, where minus a display style v-arm push, rt equals v0 fr. Cos omega p plus phi models the pulsating central pressure, A.t.o.m pulse. V-no amplitude, mega p pulse frequency, phi phase. A convenient radial kernel, fr equal frac 1 rs, e minus r rs, or fr equals frac 1 plus rs square gamma. Rs is pushback sphere scale, gamma g1. Sign, choose v0 for an outward push, repulsive, or v00 for attractive compression. A.t.o.m logic often uses large central compression, take v0, deep oscillating well. Display style v for m torsion r theta phi equals frac kappa r squared t theta phi. This mirrors angular couplings, scales like 1 r squared to influence angular momentum. Kappa r, a radial envelope for torsion strength, e.g. kappa 0 e minus slash rho t. T theta phi encodes filament geometry, simplest forms spherical harmonic expansions. T theta phi equals sum LLTMT, TLTMT, YLTMTMT. V to n psi, optional nonlinear self-interaction modeling field feedback, e.g. cubic nonlinearity, G psi 2. Keep small to preserve linear orbital basis when desired. So explicitly, h bar partial t psi frac h bar 2m nabla 2 psi plus veto fr mega p plus phi 0 psi plus kappa r r2 theta phi psi plus g psi square 2 psi. 3. Separation strategy, Floquet plus angular eigenmodes. Because v-arm push is periodic in time, cos omega pt, use flow theory. Seek solutions, psi r theta phi t equals egmet I var epsilon t bar theta phi t with phi t equals phi t equals 2 pi omega p, is quasi-energy. For weak nonlinearity and torsion, you can expand in harmonics of omega p. Phi theta, sum nth empty square, in psi n r the phi, ether minus in omega square pt. Plugging into the equation produces a coupled ladder of time harmonic eigenvalue equations. Left, h0, var epsilon plus bar omega p, right, psi n plus frac v02 fr, psi n is 1 plus psi n plus 1 equals 0, with hat h0 equals minus frac h bar 2m nabla squared plus frac kappa r squared t phi plus g sum pq psi n pq queer, where nonlinear convolution terms appear if g any 0. If v0, small compared with typical level spacing, truncating to a few n, gives quasi-stationary orbitals, Floquet states. If v0 large, strong dressing, sidebands, phonon-like replicas appear. IV, angular structure, torsion modifies spherical harmonics. Define angular eigenfunctions by diagonalizing the torsion operator on the sphere. Hat t yt a theta phi equals tau a y theta phi, where hat t acts as multiplication by t theta phi, or a differential operator built from filament geometry. For the simple multiplicative t, the y squared ta are linear combinations of ordinary spherical harmonics ylm. Label torsion modified angular modes by AA analog of lm. Use ansatz psi n r theta equals frac unar r y squared t score a theta phi. The radial equation becomes for each Floquet harmonic n an angular label a. Left minus frac bar 2, 2m frac d squared dart squared plus VF squared NAR. Write UNAR plus frac V0 FFR big UN1R plus UN plus 1A big equals to for epsilon plus NH bar omega P UNR. Quid with varm F square eclipse frac T bar squared 2M plus frac length R squared frac kappa R square A plus G mathcal NNR. Here lambda A is an effective angular separation constant, reduces to L plus 1 when torsion is 0, tau A the torsion eigenvalue, and M mathcal NNA denotes nonlinear density contributions. Interpretation. Torsion shifts the centrifugal barrier and splits degeneracies. The pulsating push term couples radial functions between Floquet sidebands. V reductions and limits to see hydrogen analog. Static limit omega P TO0 or small V0, V0, treat T as a static effective well, V arm push AVG R equals V0 FR, and set G equals 0, kappa equals 0. Then equation becomes ordinary time-independent Schrödinger, and radial solutions are hydrogen-like if you choose V0 FR, propto minus 1R, Coulomb. But typical A.t.o.m choice is short-range exponential kernel, producing bound states that resemble hydrogen orbitals qualitatively but with different radial extents and energies. No torsion, kappa equals 0, no pulsation, V equals 0, recover free hydrogenic basis when you set Vm push R equals d frac zerum F Easterglass 4 pi var epsilon 0 R. So the A.t.o.m model smoothly connects to hydrogen when appropriate kernels are chosen. V-ice. Explicit approximate 1 as in 2p forms, example Ansetsa. When torsion and nonlinearity are small and treating V-arm push as a static effective radial well, VPR, we can use hydrogen-like functional forms but with modified length scales. Define an A.t.o.m length, A-arm A.t.o.m, like Bohr radius. A is scarum A.t.o.m, equiv frac 4 pi var epsilon 0 h bar 2 m z arm f, quad z arm f equiv z0 plus delta z v0 kappa, where E arm F and delta Z parameterize how central compression and torsion renormalize effective strength. Then zeroth order orbital shapes. Once A.t.o.m approxide R approx frac 1, script pi A arm A.t.o.m and 3, E crib minus R A arm A.t.o.m. 2p.o.m approx aligned with torsion axis. Psi 2p.m R theta phi S approx frac 1 for scort 2 pi A and R 5, R ether minus R 2A arm A Y1M theta plus text torsion corrections. Torsion corrections modify Y1M into T, score A, and scale the radial exponent. 7. Selection rules and spectroscopy. A.t.o.m predictions. The pulsation omega P produces Floquet sidebands. Transitions can absorb emit quanta of omega P, so observed spectra show multiplets spaced by omega P. Torsion splits degenerate L levels. Energies to ENA depend on torsion eigenvalue, tau A. If nonlinearity G exists, levels shift with occupation, density-dependent energy, producing self-interaction broadening. 8. Concrete parameter suggestions to experiment numerically. Choose physical scales to explore numerically. Units, SI or set bar equals 1 for simplicity. Pushback scale, RS sim 0.1 to 1 in atomic units. Amplitude V0 sim 1 10 energy units. Pulsation frequency, omega P, comparable to level spacing. Hit bar omega P, sim 0.1 atomic units. Torse. Torse strength kappa 0 small, kappa 0 0 0.01 to 0.5. Choose theta phi equals alpha y2 theta phi beta 442 theta phi for interesting splitting. Nonlinearity G small G LL1 to keep near linear orbitals. Numerical recipe. 1. Expand angular part in ordinary YLM up to L max that captures torsion geometry. 2. Discretize radial coordinate and set up the coupled Floquet matrix for harmonics, n equals n, n. 3. Diagonalize to get quasi-energies var epsilon and Floquet modes. 4. Reconstruct psi t and compute densities selection rules. IX. Example simplified special case, single harmonic truncation. Truncate Floquet to n equals 0, PM1, and torsion to a single angular mode A. The radial system reduces to a 3x3 block for each A. Begin P matrix dr var epsilon v rack to fr and 0, frac v0 to fr, and hat d var epsilon parb omega p and frac v0 to fr to 0, and frac v0 to fr, and hat dr epsilon plus 2h omega p matrix. Begin P matrix u minus 1a, u0a, u1a, and P matrix equals 0, where at dr equals d minus h bar to 2m, d frac d plus v arm f squared ar. Diagonalize numerically to see band formation and pushing splitting of the usual hydrogen levels. Physical intuition, A.t.o.m qualitative predictions, short. The pushback pulsation dresses levels, Floquet replicas, and can transiently trap or eject probability density depending on phase of the pulse. Think of the electron as intermittently compressed and released by the eternal field. Torsion breaks spherical symmetry softly. Orbitals will align with filament geometry, specific LLM mixings. Degeneracies lift in patterns determined by the angular harmonic content of T, theta, phi. Nonlinearity gives occupancy-dependent shifts and possible soliton-like localized bound states if G0, attractive nonlinearity. XI. How to proceed. Practical next steps I'd run if you want. Pick numeric units and parameter values. I suggested ranges above. Build code to solve the radial plus angular plus Floquet eigenproblem, finite differences or spectral radial basis, spherical harmonic angular truncation. Visualize densities, psi 2, for orbitals